keep going with this, we have now the way to show how Gulf Stream transport can be estimated using square root theory. So let's assume for a second that the Gulf Stream transport is just going to be dominated by the zonal wind stress variations at the northern end, because you have westerlies, strong westerlies with very weak meridional winds. So in that case, the approximation can be made that the latitudes over which the trade winds are changing is given by the scale, meridional scale of Ly. So we can write the zonal winds as a function of latitudes, cosine here, with a mean magnitude of the winds tau x. So that's the latitudinal variation. The curl of the wind stress in this case, because meridional winds are 0, is just minus tau wind x dy. And our internal or interior transport is still the integration from the east to west of v dx with our wind stress curl. And we can plug in the numbers, realistic numbers for the Pacific, and get the Kuroshio transport of about 44 Sverdrups, and you can do the same thing for the Gulf Stream section here, going from east to west. Okay, and we already looked at the hydrographic sections and the associated dynamic height, which can actually allow us to look at the geostrophic currents, and presumably we can take a zero reference line and use the dynamic method to estimate the transport as well. But using Sverdrup theory, the other thing you have to remember is that we are saying we will balance the interior transport to the western boundary. But the western boundary is narrow. It's got a certain scale, let's say of the order of a kilometer, and we have to balance the mass by squeezing in all the interior transport into this narrow western boundary. When we do that for the Gulf Stream by plugging in the appropriate numbers of winds at those latitudes, we will end up with a transport of about 30 Sverdrup, because the Pacific transport, because the Pacific is a bigger interior, its transport in the Kuroshio is larger than that in the Atlantic, which is much narrower. And the velocity you get for this kind of average transport squeezed into 1 kilometer is about 30 centimeter per second. By the way, maybe I didn't say exactly what Sverdrup is. When I said 44 Sverdrups or 30 Sverdrups of transport, that is a unit of obviously named after Harold Sverdrup. It is 1 million meter cube per second. 1 million cubic meters per second. So you can imagine that the Gulf Stream is moving 30 million cubic meter per second. In fact, in reality, the Gulf Stream velocity can be much larger, up to a meter per second, and the transport can be a order 100 Sverdrups, because there are a lot of recirculating circulations happening with the nonlinear frictional boundary current that goes unstable and entrains these recirculating gyres. So at any latitude, you might end up getting much more, 3 times more than the 30 Sverdrups that we are estimating just using the Sverdrup circulation. Let's look at the currents we have seen before. We have the Antarctic circumpolar current here, transitioning into the weak subtropical gyre currents, and then we had the south equatorial current and the small south equatorial countercurrent with a strong or the doldrums here, strong north equatorial countercurrent, strong north equatorial current, and the North Pacific current, which is the extension of the Kuroshio into the open ocean after it separates from the coast, right? It's a boundary current that at some point separates. Where does it separate? Obviously, we can use the wind stress curl to see that the separation happens where the wind stress curl changes sign, which means it goes from one sign to the other, which means it's zero. So where the wind stress curl goes to zero, the gyres become separated. Okay, that's what the western boundary separation coming out of the Sverdrup theory is. Okay, there is the westerly winds in the southern hemisphere and northern hemisphere. There are the northern hemisphere trades, southern hemisphere trades, and the equatorial doldrums where the winds converge and you have very weak winds, where they obviously, when winds converge, they go to zero in the middle, right? So you do the Sverdrup theory again, integrating from the east coast. Obviously, we have set the stream function to be zero on the eastern boundary, and we are not closing them here, taking them all the way to the western boundary, because we can only impose one boundary condition in this linear first order equation. And you can see that the southern subtropical gyre is counterclockwise, because in the southern hemisphere cyclonic flow is counterclockwise or anti-clockwise. In the northern hemisphere we get clockwise anticyclonic flow, and then you have the subpolar gyres, which is not so obvious in the south because there is the connection to the Antarctic circumpolar current, and the Southern Ocean is a channel, right? So nonetheless, we get very realistic circulations, the gyres, using Sverdrup theory consistent with the wind stress curls. Again, we are only looking at the zonal winds here. And the interior transport is northward in the southern hemisphere and southward in the northern hemisphere. So the Gulf Stream northward, as we said, ends up being about 30 Sverdrups in the northern hemisphere, and whatever the number is here in the southern hemisphere. But the main point is that the value of the stream function at the western boundary is basically the estimate of the integrated interior transport, which has to be balanced by the western boundary current. Okay, so long story short, Sverdrup theory really works. You can put it in the context of a real subtropical gyre in a three-dimensional sense. So here we have the trade winds and the doldrums. There are the westerlies transitioning with the wind stress curl being zero at some point, and we have Ekman transport northward in the low latitude, southwards in the northern edge of the subtropical gyre, converging and pushing lighter water down, creating a dipping of the thermocline with a corresponding doming of the sea level. I hope you remember that still. The sea level, sea surface height, and the isopycnals, they tilt in opposite directions to cancel the pressure gradient in the deep ocean to give us very weak circulation in the deep ocean. Remember that the pressure gradients have to go to zero, and that's how we accomplish it. In the subpolar gyre, obviously you have upwelling as opposed to downwelling, so you have divergence as opposed to convergence. So the separation of the gyres again happens where the wind stress curl goes to zero. That's a lot of information coming from this simple theory, which is why we say that Sverdrup actually gave a huge push to dynamic oceanography. After he established this Sverdrup theory, dynamic oceanography became much more energized. Lots of progress was made after that, okay, especially considering Stommel also had just established the beta effect that gives us the western boundary intensification. We will look at this again when we come to the thermohaline circulation and add the other thing that we haven't said anything about yet. We've been talking about matching the interior transport with the western boundary transport, but the winds also put in vorticity into the ocean, which I may already have said, but it's cannot be said enough. So the vorticity also has to be balanced by the western boundary current. Okay, if you imagine curling your fingers around trade winds and westerlies, the sign of the vorticity is into the ocean, which means it's negative. So the western boundary has to produce positive vorticity so that the ocean doesn't keep churning faster and faster. So you have to balance the vorticity, rotational tendency of the water because of the wind stress curl as well.